You are a hologram, the physics secret of your brain that rewrites reality. You reach for a name you've said 1,000 times, and it's gone. Blank screen. Then a warm smell, yeast, sugar, heat, slides in from a doorway, and the name returns with the room, the laugh, the shoes you wore. It's like the film burned a frame and the scene reassembled itself. Here's the claim. Your memories aren't filed in your brain. They're projected from patterns, which means identity, free will, and what happens when the projector glitches aren't abstract debates. They're personal. If your life is a hologram, where are you? To see why this isn't sci-fi, we need to go back to a lab accident. Revelation, roadmap, and commitment. We're going to move in a straight line. Physics to brain, to crisis, to meaning, because the order matters. First, the physics hint. Holograms store information in waves, not in little labeled boxes. Then the brain puzzle. Decades of lesion studies failed to uncover neat addresses for memories. Yet people still remember with fewer neurons, just fuzzier. After that, the radical experiments. Tiny cues, like a scent or a chord, pull back entire scenes. The quality drops with damage, but the whole shape persists. That's hologram behavior. Here comes the twist. What you see and remember isn't the system, it's the user interface your nervous system renders to stay alive. We'll track how neural populations encode information in frequency, timing, rhythm, phase, and use interference to bind features into a single experience. That's not poetry. That's measurable oscillations and pattern completion. We'll talk about the weird and we'll keep it grounded. Non-local encoding, distributed storage, interference patterns, yes. Telepathy and magical thinking, no. We'll show how resilience and olfaction, sleep replay, and cross-frequency coupling make recall possible from fragments. We'll look at how the projector fails. PTSD's overstamped patterns, déjà vu's false completes, hallucinations, self-amplifying loops, and what that says about precision and timing. The stakes are heavy. Treatments for dementia that target timing and cues, learning strategies that exploit frequency and sleep, legal ideas about identity when the projection can be remapped, and the darkest question, what happens if the projection ends? We'll rack up falsifiable predictions, flag speculation, and mark the line between metaphor and mechanism. So where did the idea come from? Not from mysticism, from a mid-20th century lab moment when a physicist knocked a plate, ruined the edges, and still saw the whole image, just blurrier. The physics seed, how holograms work and why physicists got obsessed. A hologram is a cheat that uses waves to hide a 3D scene inside a flat plate. You don't store the picture itself, you store the way light interferes with itself, the ripples. Shine a reference beam on an object. The light bouncing off it interferes with that beam, and where crest meet crest or cancel, a high-frequency pattern freezes onto the film. It looks like static, but it's not random, it's the object transformed into frequency space. Here's the property that hooked physicists, the hole in every part trick. Cut the plate in half, and each half still reconstructs the whole image at lower resolution when lit by the original reference beam. Keep cutting, and you never get just an ear or a shoe. You get the whole person, blurrier each time. In holography, information is spread out across the medium, not stamped into precise locations. That's non-local storage. Under the hood is Fourier math. Any shape can be expressed as a sum of waves at different frequencies and phases. The interference pattern on the plate is a Fourier domain encoding of the scene. The reconstruction is the inverse, transform, done by light itself when you shine the right beam. No CPU, no lookup table, physics does the math. If a smudge erases a region of the plate, you lose some frequencies, so fine detail and contrast suffer. But the global structure survives because other parts still carry overlapping information. Now for the coffee spit moment. A researcher cracks a holographic plate, curses, tapes a fragment to test the damage, and lights it. The whole object floats there, ghostly but intact. That is the moment your gut learns something your head hasn't caught up with. In wave-encoded systems, damage degrades fidelity, not categorical presence. That's a different failure mode than a hard drive, where a missing sector deletes a specific file. Physicists got obsessed because holography taught them two things. One, information can be represented in frequency rather than place. Two, interference makes storage and computation happen through superposition. Many components mingle in the same medium without overriding each other, as long as their frequencies and phases are handled correctly. You can even pack multiple holograms into one plate by changing the reference beam's angle. Tilt the beam back the right way, and you retrieve the one you want. That's multiplexing, a concept that jumps easily to signals, radios, and yes, neural rhythms. Stakes? If a biological system used anything like this, damage wouldn't delete grandma's cookie recipe and leave your piano lessons untouched. It would blur everything a little, then more, then a lot. Fragmentary cues could still unlock whole scenes, but with reduced clarity. Bits of the object would be recoverable from many places because the code wasn't about location, it was about frequency and phase. Engineers also loved how holograms naturally filter noise. Because reconstruction requires the right reference beam, random light doesn't easily read the image. And because detail lives in high frequencies, a partial loss mostly hits fine structure first. The system degrades gracefully. That word, gracefully, is code for robust in the face of damage, a trait evolution tends to favor. Meanwhile, the math behind holography, Fourier transforms, and Gabor functions started showing up in sensory science in the late 1940s and 1950s. Edge detectors envision receptive fields that look like little rippled patches, all suspiciously similar to the kernels used to analyze images in frequency space. When you see a neuron respond to specific orientations and spatial frequencies, you're watching a biological tissue act like a tiny filter, passing some waves and ignoring others. But hold the brakes. A hologram is made of light in a carefully controlled setup. The brain is warm, wet biology. The claim isn't that your cortex is literally a laser plate. The claim is that wave-based encoding, distributing information over frequency and phase, creates properties we can test, whole in every part. Like resilience, pattern completion from partial cues, graceful degradation of detail, and multiplexing by timing. Think about multiplexing for a second. In optics, you store multiple images in one plate by altering the reference beam's angle. In signal processing, you stack channels in different frequency bands. In the brain, you see multiple rhythms, slow theta, fast gamma, coupling, so features can travel together without crashing into each other. If those rhythms act as the angles of a biological reference beam, you can layer content in the same tissue and call it later by timing. Here's a micro story to land it. A graduate student drops a coffee mug onto the table, holding a hologram test. Crack, swear, paper towels, the usual. When the room calms down, they put a broken shard in the mount, switch on the beam, and watch a tiny, hazy teapot hover in the air. Still three-dimensional, still there. That image sticks because it rewires your expectation. A broken thing that still contains the whole. One more detail that matters. Fourier space doesn't care about where a feature is. It cares about which frequencies compose it. Shift the scene in space, and its Fourier magnitude barely changes. You alter phase instead. That separation, content in magnitudes, placement in phase, is a power move. It means the system can represent what and where differently. Later, when we look at how brains bind features into a unified percept, phase will be doing quiet, essential work. So physicists left the optics lab with a toolbox: interference, superposition, Fourier representations, and multiplexing. The question drifted into neuroscience, like a seed with burrs. If a brain harnessed wave codes, would its memories behave more like files or like holograms? Meanwhile, in clinics and animal labs, something stubborn refused to fit the file cabinet model. While that was happening in physics, a different kind of accident kept happening in neuroscience, especially through the 1940s, 1960s. Remove tissue here, and nothing specific vanishes. Everything just gets a little worse. The neuroscience puzzle, Lashley's Engram hunt, and the missing address. To understand why brains don't act like hard drives, we need to sit with a man who tried to find the file cabinet and came up empty. Carl Lashley spent decades cutting, scorching, and carefully removing bits of rat cortex to find the engram, the physical address of a learned memory. The setup was simple and brutal. Train a rat to run a maze, let it prove the skill is solid, then lesion a region and test again. If memory is a thing with the home, damage the home and the behavior should collapse in a specific way. But the collapse never behaved. Rats with damage to one area could still run the maze, slower, sloppier, but not erased. Move the lesion elsewhere, same story. You could carve lots of cortex and the rats got worse in proportion to how much tissue they lost, not where you took it from. Lashley called it mass action, the idea that the cortex works as a whole to support complex behaviors. He paired it with equipotentiality. Remaining tissue can take over functions, at least partially. What he didn't find was a mailbox labeled maze memory, back left drawer. Here's the human angle. Stroke. Survivors can lose swaths of cortex and end up with blurred abilities, not a single cleanly deleted memory. A face that used to snap into recognition now stalls. Feels familiar but won't resolve. A word sits just out of reach, not wiped, just misindexed. It's the same signature Lashley saw in animals. Performance degrades with volume of loss, not with precise coordinates. That's not how you'd expect it to look if memory lived in discrete parcels. Lashley's failure wasn't a dead end, it was a signal. If engrams weren't sitting in one spot, maybe they were patterns. Distributed, overlapping, and resilient. He lacked the tools to see patterns. The mid-century cortex was a black box. Action potentials along axons were easy to record. The subtle ballet in dendritic webs was not. So Lashley's conclusion was cautious and maddening. "I sometimes feel," he wrote, "that the necessary conclusion is that learning is just not possible." He didn't mean it literally. He meant the model on offer, engrams as local stamps, didn't fit the data. Meanwhile, micro-stories from clinics kept whispering the same thing. A patient loses part of the temporal lobe and struggles with names, yet give them a smell from their childhood kitchen and an entire Sunday afternoon returns. The checkered tablecloth, the scrape of a chair, the rhythm of a parent's footsteps. Clarity isn't perfect, edges are smudged, but the scene is whole. Another patient's stroke leaves their speech halting, yet a familiar song lets them sing full lines. Function routes around damage. The pattern seems intact, but harder to access. This was the moment everything changed. Not because a single experiment answered the engram question, but because the failure to find addresses forced a pivot in language. Instead of "where is the memory?" the better question became, what population dynamics sustain this memory? If performance loss scales with tissue loss, we're looking at codes smeared across networks. If partial cues can trigger full recall, we're looking at pattern completion. There was one problem, without a map of microstructure. Pattern sounded like hand-waving. Lashley's critics wanted specifics. Which neurons, which layers, which signals? The answer would have to wait for new methods, multi-unit recordings, better lesion controls, and computational models that could test how distributed codes behave under damage. But the broad shape of Lashley's law kept showing up. Across tasks, the severity of impairment tracked the amount of cortex removed. The missing address wasn't hiding, it was the wrong metaphor. From the rat room, we can jump to a kitchen table to see how this felt. Get this, researchers would lesion one hemisphere and watch rats struggle a bit, then train them again. With time, performance improved. Add a second lesion and the animals dipped, then clawed back again. The behavior was plastic. Memory as a static trace didn't explain the rebound. Memory as a dynamic pattern, constantly re-engraved by use, did. What nobody knew at the time was that the cortex's fine-fibered dendritic webs were exquisitely tuned to rhythms, the very stuff of waves. Lashley couldn't measure those rhythms, but he could see their consequences: graceful degradation, redundancy, and the absence of a single point of failure. His maze data were the behavioral shadow of a system organizing information in a distributed code. While that was happening in animal labs, neurosurgeons started to map human functions with electrical stimulation during awake surgery. Touch one spot, a patient tasted metal. Touch another, a memory fragment fluttered up, partial, noisy, rarely a full delete or full play. The brain felt less like a library of books and more like a chorus that could hum the whole tune with fewer singers, just not as sharply. To understand why that chorus could hold a song without a single soloist, we need a tool Lashley didn't have, a way to look at signals in frequency and phase. That would arrive with Carl Pribram and the math of Fourier transforms, an invitation to see the cortex not as storage slots, but as a medium where interference patterns carry content. Frequency brains, Pribram, Fourier transforms, and the cortex as a hologram. Carl Pribram walked into this puzzle from surgery suites and psychology labs, not from an optics bench. He kept seeing the same mismatch. Action potentials along axons explained fast messages, but perception had textures that felt wave-like. Context, blending, the way a whole scene snaps in from a hint. He turned to Dennis Gabor's mid-20th century mathematics and asked a blunt question. What if the cortex represents information in frequency and phase, then reconstructs experience by interference? To see why that isn't airy, look at the cortex's microarchitecture. Under the microscope, you don't just find long cables firing all or none spikes. you find fine, branchy dendritic webs that sum inputs in gradients and, crucially, resonate. Those dendrites, layered through cortex, form receptive fields that behave like filters. They respond best to certain orientations and spatial frequencies in vision, certain modulations in sound, particular temporal rhythms in touch. In other words, they look like biological Gabor filters, little rippled patches that carve the world into frequency components. Here's where Fourier transforms enter the story. Any image can be decomposed into sinusoidal gratings at different spatial frequencies and orientations. In primary visual cortex, neurons are tuned to exactly those gratings. Present a bar tilted 15 degrees and one set fires. Shift the bar and a different pattern lights. Shift the bar's position without changing its frequency content, and the overall strength of responses hardly changes. What changes is timing and phase relationships. That division, content carried in frequency selectivity, placement adjusted by phase, tracks the hologram math Pribram leaned on. But he didn't just make a metaphor. He pointed to mechanisms. Population activity across columns and layers generates oscillations. When you measure local field potentials, you see rhythms spanning slow theta to fast gamma. These rhythms aren't background noise. They gate when neurons can influence each other. Two assemblies firing in sync at a particular phase couple more strongly than ones out of phase. That's interference in biological tissue, superposition, and timing, determining what pattern wins. The stakes are immediate for perception. Think about edges. Your retina sends a messy, contrast-limited signal. Cortex sharpens it by aligning responses to specific spatial frequencies, then combining them. If phases across those frequency channels lock in a consistent relationship, you experience a crisp contour in the surface that belongs to it. If the phases drift, the contour loses snap. This is why a visual illusion can push your system to interpret the same intensities as different shades. Your brain is reconstructing from frequency cues and priors, not passively reading pixels. Now remember Lashley's puzzle. Remove tissue and behavior degrades with amount, not place. Frequency domain codes explain that signature. If the what of a scene lives across populations tuned to many frequencies, then slicing out any subset removes some bands. Fine detail fades first. The gist persists. You don't need a single neuron labeled grandmother to fail spectacularly. You need a distributed loss that erodes the spectrum that defines her face, her voice timbre, the cadence of her walk. Pushback came fast. Isn't this just a fancy analogy? Pribram answered by pointing at concrete correspondences. The mathematics used to describe ideal receptive fields. Gabor wavelets, Wigner distributions are also used in optics to analyze holograms and diffraction. Early studies mapped cortical responses to two-dimensional Fourier components, not just point-by-point features. And later, multi-electrode recordings showed something deeper. The timing of spikes relative to ongoing rhythms can carry as much information as the spikes themselves. Phase of firing codes allow a neuron to say different things without changing its rate, like writing multiple messages on one carrier wave. Here's where the cortex as hologram claim earns its nuance. No, the brain isn't storing optical interference patterns. Yes, it's building interference patterns in electric fields and synaptic currents. These fields bias which inputs sum constructively and which cancel. A memory in this view isn't a fixed trace, it's a stable attractor, a pattern of synchronized activity that can be re-entered when the right partial cue nudges the system. You shine the reference beam of ongoing rhythms through a fragment, and the full pattern settles in. Consider multiplexing. In optics, you angle the reference beam differently to pack multiple holograms into one plate. In cortex, you can couple different content to different phases or frequencies. Theta cycles in the hippocampus can bracket sequences. Nested gamma bursts can bind features within each moment. Adjust the phase, and you retrieve a different chunk of the sequence. That's not philosophy, it's been measured as theta. Gamma coupling during memory tasks and replay during sleep. The human feel of this shows up in micro-stories. Someone hears 3 piano notes, do-re-mi, and suddenly the kitchen from 1998 unfolds. The notes aren't the picture. They're a key that lines up phases across frequencies in auditory and association cortex. Once alignment crosses a threshold, the larger pattern completes. If the underlying circuits have lost high-frequency precision, aging, trauma, disease, the same key yields a hazier scene. That's pattern completion and graceful degradation in lived time. Pribram didn't ignore alternatives. He compared his holonomic account with models focused on spike timing propagation along axons. He argued they're complementary. Axons carry packets, dendritic and field. Dynamics shape the carrier's meaning by aligning or misaligning phases. He also drew a boundary around quantum talk. Yes, the math overlaps with quantum formalisms, but you don't need long-lived quantum coherence in neurons to get interference in classical fields.